Close your eyes and imagine a universe governed by clear rules, mathematical laws that dictate how matter behaves, how planets form, and how solar systems take shape. For centuries, astronomers believed these rules were well understood. Planets formed from disks of gas and dust, settled into stable orbits, and followed predictable patterns based on mass, composition, and distance from their star. The universe seemed orderly and comprehensible. Then came the discovery of exoplanets. Thousands of distant worlds, each more surprising than the last. We found planets that shouldn't exist according to our models, gas giants orbiting dangerously close to their stars, rocky worlds larger than theory allowed, entire systems arranged in ways that defied everything we thought we knew about planetary formation. Tonight, we journey to these seemingly impossible worlds. Not planets that break the laws of physics, but planets that break our understanding of them. They force us to reconsider assumptions, reminding us that our theories are approximations, not final truths. The laws of physics remain intact. It is our interpretation that evolves. From the safety of Earth, let yourself drift through these cosmic anomalies. There is something comforting in realizing the universe still holds mysteries, that science is an ongoing exploration rather than a finished story. These planets teach us humility. They show that when observation conflicts with theory, observation always wins. So relax, breathe deeply, and prepare to explore worlds that shouldn't exist but do. The universe is far stranger than we imagined, and that strangeness is not a flaw, it is a gift. Our journey begins with a mystery that revolutionized our understanding of planetary systems and forced us to completely reimagine how planets form and migrate. This is the story of hot Jupiter's gas giants orbiting their stars at distances closer than Mercury orbits our Sunday. When astronomers developed theories of planetary formation in the mid-20th century, they based their models on the only example they had, our solar system. In our system, small rocky planets orbit close to the Sun, Mercury, Venus, Earth, Mars. The gas giants Jupiter, Saturn, Uranus, Neptune orbit much farther out in the cold outer regions of the solar system. This arrangement made perfect sense according to our understanding of how planets form. In the protoplanetary disk around a young star, temperature decreases with distance. Close to the star, it's too hot for volatile compounds like water, methane, and ammonia to condense. Only rocky materials and metals can solidify. This is why the inner planets are small and rocky. Beyond a certain distance, the frost line, it's cold enough for ices to form. With more solid material available, planetary cores can grow larger. Once a core reaches about 10 Earth masses, it can gravitationally capture enormous amounts of hydrogen and helium gas from the disk, becoming a gas giant. This model predicted that gas giants must form in the outer regions of planetary systems, beyond the frost line. Close to the star, there simply isn't enough solid material to build cores massive enough to capture gas. Rocky planets would form in the inner system, gas giants in the outer system. This was considered a fundamental principle of planetary formation. Then, in 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. This planet orbited a Sun-like star about 50 light-years from Earth. But something was profoundly wrong. The planet had about half the mass of Jupiter, clearly a gas giant. Yet it orbited its star once every 4.2 days, at a distance of only about 0.05 AU, 8 times closer than Mercury is to our Sunday. The astronomical community was stunned. This couldn't exist according to theory. At that distance, the temperature would be over 1,000 degrees Celsius. Any gas should have been blown away during the planet's formation. There wasn't enough solid material at that distance to build a gas giant core. According to everything we thought we knew, 51 Pegasi b was impossible. Some astronomers initially suggested the detection was an error, perhaps a pulsation in the star being misinterpreted as a planet. But as the observations continued, it became clear the planet was real. And it wasn't alone. More hot Jupiters were discovered in rapid succession. HD 209458b orbiting its star every 3.5 days. Tau Botis b completing an orbit in just 3.3 days. WASP 12b orbiting in a mere 26 hours. Each discovery reinforced an uncomfortable truth. The universe was producing planets that our theories said couldn't exist. The existence of hot Jupiters forced a complete reconceptualization of planetary formation. These planets couldn't have formed where we found them, but they could have formed farther out and then migrated inward. This migration would have to involve interaction with the protoplanetary disk or with other planets, causing the gas giant to spiral inward toward its star over millions of years. This process, called planetary migration, was known theoretically but was thought to be rare. Hot Jupiters proved it was common, perhaps even typical for gas giants in other systems. Our solar system, with its gas giants remaining in the outer system, might be the exception rather than the rule. HD 80606b takes the hot Jupiter paradox even further. This gas giant orbits its star in a highly elliptical orbit, varying from 0.03 to 0.88 AU, sometimes closer than Mercury, sometimes farther than Venus. This orbit is so eccentric, so elongated, that it defies explanation. How did a gas giant end up in such a stretched orbit? The leading theory involves gravitational interactions with a second planet that was later ejected from the system, but the details remain mysterious. WASP 12b presents another impossibility. This planet orbits so close to its star that tidal forces have stretched it into an egg shape. The star is literally consuming the planet's atmosphere, which is being stripped away and devoured at a rate suggesting the planet will be completely consumed in about 10 million years. Before we discovered WASP 12b, such rapid planetary destruction was considered unlikely. Now we know it happens. Kelt 9b breaks multiple rules simultaneously. It's a gas giant orbiting so close to a massive blue star that its daytime temperature exceeds 4,300 degrees Celsius, hotter than many small stars. At these temperatures, molecules can't survive. Even hydrogen exists as individual atoms. The planet should have had its atmosphere completely blown away long ago, yet it persists, though likely losing mass rapidly. It exists in a state that theory suggested should be unstable, yet it's been stable for millions of years. The hot Jupiters teach us that planetary systems are dynamic, violent, chaotic places. Planets don't simply form and remain where they started. They migrate, collide, eject each other, interact gravitationally in complex ways. Our solar system's orderly arrangement is unusual, perhaps even rare. Most systems apparently experience far more dramatic evolutionary histories. These worlds also teach us about the limits of theory. Before we observed hot Jupiters, our formation models were elegant and logical and incomplete. They accurately described our solar system but failed to predict the diversity of configurations the universe actually produces. Observation must guide theory, not the other way around. When reality contradicts our models, we change our models, not reality. As you contemplate these impossible giants orbiting impossibly close to their stars, imagine the violence of their formation and migration. Imagine young gas giants spiraling inward through dusty disks, losing angular momentum, falling toward their stars. Imagine the heating, the atmospheric loss, the tidal deformation. These planets are survivors of chaotic histories, witnesses to processes we're only beginning to understand. They shouldn't exist, yet here they are, teaching us that the universe plays by rules more subtle and complex than we first imagined. Moving beyond orbital anomalies, we encounter planets whose physical properties seem to violate our understanding of matter itself. These are worlds that are too puffy, too dense, or too variable planets, whose existence challenges what we thought we knew about how matter behaves under extreme conditions. Kepler 7b is a planet that shouldn't be able to hold itself together. This Saturn-sized world orbits its star every 4.9 days at a distance that subjects it to intense stellar radiation. But what makes Kepler 7b extraordinary is its density, or rather, its lack of density. The planet has an average density of about 0.16 grams per cubic centimeter, roughly equivalent to styrofoam or balsa wood. To put this in perspective, Saturn, often called the least dense planet in our solar system, has a density of 0.69 grams per cubic centimeter. Kepler 7b is less than 1/4 as dense. If you could find an ocean large enough, Saturn would float. Kepler 7b would float much higher in the water. For a planet the size of Saturn to have such low density, it must be almost entirely hydrogen and helium, with almost no heavy elements, heated until it swells like a balloon. According to our models of planetary structure, planets this puffy shouldn't be stable. The intense radiation from their nearby stars should cause their atmospheres to evaporate rapidly. The low density suggests the planet is barely held together by its own gravity. Yet Kepler 7b exists, stable enough to have survived for millions or billions of years. It's not a transient phenomenon, but a persistent configuration of matter that our theories struggle to fully explain. HATP 1b presents a similar challenge. This Jupiter-sized planet has a density of just 0.12 grams per cubic centimeter, even lower than Kepler 7b. It's one of the puffiest planets known. The planet orbits its star every 4.5 days and receives intense stellar radiation that heats it to over 1000 degrees Celsius. This heating causes the atmosphere to expand dramatically, but the mechanism by which it maintains such extreme expansion without losing its atmosphere entirely remains poorly understood. Several theories attempt to explain these ultra-low density planets. One suggests that tidal heating energy deposited in the planet's interior by tidal forces from the nearby star provides additional heat that puffs up the planet. Another proposes that the planets have deep wind systems that transport heat from the irradiated day side to the interior, preventing normal contraction. A third suggests that the planets possess strong magnetic fields that interact with stellar wind to deposit energy in their atmospheres. Each theory has strengths and weaknesses. No single mechanism fully explains all the puffy planets we've discovered. It's possible that different planets maintain their puffiness through different mechanisms, or that multiple mechanisms work together. What's clear is that these planets exist, defying our initial predictions about how gas giants should behave under intense stellar irradiation. At the opposite extreme, we find planets that are impossibly dense. GJ 367b is a small planet only slightly larger than Mars, orbiting a red dwarf star. But this tiny world has a density of about 8.1 grams per cubic centimeter, nearly twice Earth's density. For comparison, iron has a density of 7.9 grams per cubic centimeter. GJ 367b is denser than solid iron. How can a planet be denser than iron? The answer involves the planet's composition and internal pressure. GJ 367b likely has an enormous iron core making up about 86% of its mass. The remaining material is probably a thin rocky mantle. The immense internal pressure caused by the planet's gravity compressing its interior increases density even further. Matter under extreme pressure occupies less volume than at normal pressure, increasing density beyond what the materials would have at Earth's surface. But even accounting for pressure, GJ 367b's extreme density challenges our models. How did a planet form with such an iron-rich composition? Did it form as part of a larger planet that lost its rocky mantle in a giant impact, leaving just the iron core? Or did it form in an unusually metal-rich region of its protoplanetary disk? We don't have definitive answers, only intriguing possibilities. TOI 849b presents a different density puzzle. This Neptune-sized planet has no atmosphere, just a bare rocky or metallic core exposed to space. It's essentially a planetary core without any envelope, orbiting its star every 18 hours. Something catastrophic happened to this world. Either it formed as a gas giant and lost all its atmospheric gas, or it's the remnant of a failed gas giant that never captured an atmosphere, or it collided with another planet and was stripped down to its core. Whatever happened, TOI 849b now exists in a state that shouldn't be stable. A bare planetary core at such a close orbital distance should either be evaporating rapidly under stellar radiation or should be capturing gas from the stellar wind to rebuild an atmosphere. Yet, TOI 849b remains bare, neither gaining nor losing material at rates we can detect. It persists in an apparently unstable configuration, challenging our understanding of planetary atmospheres and their stability. 55 Cancri E adds another layer to the density mystery. This super-Earth has a density suggesting a carbon-rich composition rather than the oxygen-rich silicates that dominate Earth's composition. Models suggest the planet might have a core of diamond crystallized carbon formed under immense pressure. If confirmed, this would require a formation process entirely different from any planet in our solar system, arising in a carbon-rich protoplanetary disk, unlike the oxygen-rich disk that formed our solar system. These density anomalies remind us that planets can be made from various ingredients and form under diverse conditions. Earth-like planets are not the only possibility, perhaps not even the most common. The universe experiments with planetary compositions we're only beginning to catalogue. Each density extreme, whether impossibly puffy or impossibly compressed, teaches us something about the range of conditions matter can adopt in planetary environments. As you contemplate these density anomalies, imagine matter behaving in unfamiliar ways. Imagine gas planets expanded like cosmic balloons, barely holding together. Imagine compressed cores denser than iron, matter squeezed by its own gravity into configurations impossible to recreate on Earth. These planets are natural laboratories, showing us what matter does under conditions we can barely simulate, existing in states we're still learning to understand. One of the most fundamental assumptions about planetary systems was that planets should orbit in the same direction as their star rotates. This made perfect sense. Planets form from a rotating disk around a young star, and conservation of angular momentum dictates that everything should spin the same way. In our solar system, all 8 planets orbit the Sun in the same direction, the direction of the Sun's rotation. This seemed like a universal rule. Then we discovered planets orbiting backward. HATP 7b was one of the first planets found to have a retrograde orbit. It circles its star in the opposite direction to the star's rotation. This discovery was shocking. How could a planet orbit backward? It seemingly violated conservation of angular momentum, one of the most fundamental principles in physics. The answer involves gravitational chaos. HATP 7b likely formed in a normal prograde orbit, but was later perturbed by gravitational interactions with another massive planet or a stellar companion. These interactions can flip a planet's orbit, sending it careening in the opposite direction. The process requires precise conditions and tremendous energy, but it's possible. WASP-17b takes retrograde motion to an extreme. This puffy gas giant orbits backward and is also highly inflated, one of the largest planets known. The retrograde orbit suggests a violent history, possibly involving close encounters with other planets that also explain its unusual size. The planet exists in a configuration that our early models said was forbidden, yet there it is, majestically circling its star in the wrong direction. Kepler 5, 6b and c present an even stranger configuration. These two planets orbit in planes tilted about 45 degrees from their star's equatorial plane. Not backward, but severely misaligned, like planets orbiting above and below the star rather than around its equator. The cause appears to be a distant companion star that gravitationally torques the planetary system, tilting the orbital planes over millions of years. Before discovering these misaligned systems, we assumed that planetary orbits should always align with their star's rotational equator. The protoplanetary disk should be aligned with the star's rotation, and planets forming in that disk should therefore orbit in the star's equatorial plane. These misaligned systems show that gravitational perturbations can drastically alter orbital configurations long after formation. HD 80606b, mentioned earlier for its extreme orbital eccentricity, also has a significantly tilted orbit relative to its star's equator. The planet's orbit is inclined by about 42 degrees. Combined with its highly elliptical path, this creates a complex three-dimensional orbital dance, unlike anything in our solar system. Understanding how this configuration arose requires invoking multiple planetary interactions, likely including planets that were ejected from the system entirely. The prevalence of retrograde and misaligned orbits has forced us to reconsider the stability of planetary systems. We once thought that once planets formed, they would remain in relatively stable orbits for billions of years, barring major catastrophes. But these anomalous orbits suggest that many, perhaps most planetary systems go through violent reorganizations. Planets migrate, collide, gravitationally scatter each other, and sometimes end up in configurations that seem impossible. Some binary star systems host planets with even more complex orbital configurations. Planets can orbit one star while a second star orbits nearby, creating gravitational perturbations that vary as the two stars orbit each other. Or planets can orbit both stars in a circumbinary configuration, experiencing constantly changing stellar radiation as they circle the binary pair. These complex gravitational environments can produce orbital configurations impossible around single stars. PSRB 1257 plus 12, a pulsar with multiple planets, presents perhaps the most extreme example of orbital reconfiguration. These planets orbit a neutron star, the collapsed core of a star that exploded as a supernova. Any planets that existed before the supernova would have been destroyed or ejected by the explosion. The current planets, likely formed after the supernova from the debris of the explosion, or from material from a companion star torn apart by the pulsar. Their orbits are remarkably coplanar and nearly circular, suggesting they formed in a disk, but a disk created after a stellar cataclysm, not during normal star formation. These retrograde and misaligned worlds teach us that planetary systems are not static, but dynamically evolving. They go through phases of instability, violence, and rearrangement. Many systems probably started with more planets than they currently have, with some planets being ejected into interstellar space during these chaotic phases. The survivors end up in whatever orbits they happen to occupy when the system finally stabilizes. Our solar system appears to have experienced its own instability period, called the Late Heavy Bombardment, about 4 billion years ago. During this time, the giant planets' orbits shifted, triggering a cascade of collisions and ejections in the asteroid and Kuiper belts. Some researchers even suggest there might have been a fifth giant planet that was ejected during this event. If true, our orderly solar system is the result of ancient chaos, not pristine stability. As you contemplate these backward and tilted worlds, imagine the violent histories they encode. Imagine planets approaching each other gravitationally, swinging past in close encounters that fling one planet inward, another outward, another into a backward orbit. Imagine the chaos of planetary systems in their adolescence, before settling into the configurations we observe today. These anomalous orbits are scars from ancient battles, memories of violence written in celestial mechanics. In our solar system, there's a clear gap in planetary sizes. We have small, rocky planets. Earth is the largest at 1 Earth mass, and we have gas giants, Neptune. The smallest giant has 17 Earth masses. There's nothing in between. This gap seemed natural below a certain mass. Planets can't capture significant amounts of hydrogen and helium. Above that mass, they become gas giants. Simple. Then we started finding planets in the forbidden zone. Super-Earths are rocky planets larger than Earth, but smaller than Neptune. Mini-Neptunes are smaller versions of Neptune, with significant gas envelopes, but not quite massive enough to be called gas giants. These planets, occupying the size range from about 1 to 4 Earth radii, are apparently the most common type of planet in the galaxy. Yet they don't exist in our solar system. Kepler 10c was one of the first super-Earths discovered. This planet has a radius about 2-3 times Earth's and a mass about 17 times Earth's. Calculations suggest it's predominantly rocky, essentially a scaled-up Earth. But according to our formation models, a planet that massive should have captured a thick hydrogen-helium atmosphere, becoming a Neptune-like world. Instead, Kepler 10c is rocky all the way through, or at least has only a very thin atmosphere. How is this possible? One theory suggests the planet formed in a region of the protoplanetary disk that was depleted of gas, preventing it from capturing a thick atmosphere. Another proposes that it formed with an atmosphere but lost it to stellar radiation or a giant impact. A third suggests that we're simply wrong about the mass threshold at which planets capture thick atmospheres. It might be higher than we thought, or it might depend on factors beyond mass alone. LHS 1140b presents a similar mystery. This super-Earth orbits in its star's habitable zone, the distance where liquid water could exist on the surface. It has about 6.5 times Earth's mass and 1.4 times Earth's radius, making it very dense, likely dominated by iron and rock. But a planet this massive, forming in a region where water could exist as ice during formation, should have captured a thick atmosphere. Yet LHS 1140b appears to be predominantly rocky, with at most a thin atmosphere. The mini-Neptunes present the opposite puzzle. These planets have masses of 5 to 10 Earth masses, but radii of 2 to 4 Earth radii. Their low density indicates they possess significant gas envelopes of hydrogen and helium, but they're too small to have captured these envelopes through the standard gas giant formation mechanism. How did they acquire their atmospheres? One possibility is that these planets initially formed larger cores that did capture thick atmospheres, but then lost much of that gas to stellar radiation, leaving behind the mini-Neptune we see today. Another is that they captured their atmospheres through a different mechanism than gas giants, perhaps accreting gas more slowly over longer periods. A third suggests that our understanding of core sizes needed to capture gas is incomplete. The Kepler mission discovered that super-Earths and mini-Neptunes often occur in tightly packed orbital configurations, with multiple planets orbiting closer to their stars than Mercury does to our Sunday. These compact multi-planet systems are common around other stars but don't exist in our solar system. Why not? One theory proposes that Jupiter's formation prevented super-Earths from forming in our solar system's inner regions. Jupiter may have scattered material around, disrupting the accumulation of larger rocky planets close to the Sunday. Alternatively, Jupiter's migration history might have cleared out the inner solar system before super-Earths could form. Without Jupiter's influence, our solar system might have looked very different, possibly hosting multiple super-Earths in the inner system. K218b highlights another puzzle. This mini-Neptune orbits in its star's habitable zone, and spectroscopic observations have detected water vapor in its atmosphere. But is this planet habitable? With 8.6 Earth masses and 2.6 Earth radii, it likely has a rocky core surrounded by a thick hydrogen-helium atmosphere. Any liquid water would be beneath this atmosphere, perhaps at the base where pressures are enormous. Could life exist in such an environment? We don't know. It's a type of world we have no experience with. TOI 1452b adds yet another wrinkle. This super-Earth has a density suggesting it might be a water world, a planet where water makes up a significant fraction of the total mass. Not just surface oceans, but potentially global oceans hundreds of kilometers deep, possibly overlaying exotic high-pressure ices formed deep in the planet's interior. Such planets were predicted theoretically, but finding actual candidates was unexpected. The diversity of super-Earths and mini-Neptunes suggests that planet formation in the 1 to 10 Earth mass range is highly variable. Small changes in formation conditions the amount of gas available, the timing of formation relative to gas dispersal, the planet's orbital distance. Interactions with other planets can produce wildly different outcomes. This range appears to be a transition zone where planets can go many different ways. Our solar system's lack of super-Earths and mini-Neptunes now appears to be the anomaly, not the norm. Most stars seem to host planets in this size range. Our orderly arrangement of small, rocky planets and distant gas giants is unusual, possibly even rare. This has profound implications for understanding planetary formation. The models we developed based on our solar system apparently describe a special case, not the general case. As you contemplate these planets in the forbidden zone, Imagine worlds scaled up from Earth, but not just bigger Earths. Imagine the diversity of outcomes possible in the 1 to 10 Earth mass range. Rocky super-Earths with crushing gravity, mini-Neptunes with thick gas envelopes, water worlds with global oceans, and configurations we haven't yet imagined. These planets occupy a size range to our solar system skipped, showing us possibilities we never anticipated. They shouldn't exist according to our models, yet they're everywhere we look, teaching us that nature is more inventive than our theories. Beyond individual planetary anomalies, we've discovered entire planetary systems arranged in configurations that seemed impossible before observation proved otherwise. These are systems where the architecture itself defies our expectations, where multiple planets interact in ways that shouldn't be stable, where the arrangement challenges what we thought we knew about celestial mechanics. TRAPPIST-1 is perhaps the most famous example. This ultra-cool red dwarf star hosts 7 Earth-sized planets, all orbiting within a distance smaller than Mercury's orbit around our Sunday. 3 of these planets orbit in the habitable zone where liquid water could exist. The entire system could fit inside the orbit of Mercury, yet it's stable, with planets not colliding or ejecting each other. According to our understanding of planetary system stability, such tightly packed systems should be unstable. Planets orbiting so close together should gravitationally perturb each other, causing orbits to become increasingly eccentric until planets collide or are ejected. Yet TRAPPIST-1's planets have orbited stably for billions of years. How? The answer lies in orbital resonances. The TRAPPIST-1 planets are locked in a complex chain of orbital resonances, where the orbital periods of adjacent planets are related by simple ratios. For example, for every 8 orbits of the innermost planet, the second planet completes 5 orbits, the third planet about 3 orbits, and so on. These resonances stabilize the system, preventing close encounters that would destabilize the orbits. But creating such a perfectly tuned resonance chain seems improbable. The planets would have to migrate into these specific orbits and remain locked in resonance. One planet leaving the resonance chain would destabilize the entire system. Yet, TRAPPIST-1 exists, a 7-planet resonance chain that shouldn't be stable but is, challenging our probabilistic expectations of planetary system evolution. Kepler 3-6b and c present a different stability puzzle. These 2 planets orbit a Sun-like star, but they pass within 1.2 million miles of each other every 97 days, about 5 times the Earth-Moon distance. One planet is rocky Kepler 3-6b, the other is a mini-Neptune, Kepler 3-6c. When they pass each other, they experience strong gravitational interactions that should, over time, destabilize their orbits. Yet they've maintained this configuration for millions or billions of years. HD 10180 potentially hosts 9 planets, though the outer planet's existence is debated. If all 9 exist, this system would have more planets than our solar system. The planets are tightly packed, with several in orbits smaller than Mars's orbit around the Sunday. Creating such a system requires precise formation conditions, and maintaining its stability requires fortunate orbital configurations. It exists at the edge of what celestial mechanics allows. Binary star systems present their own stability challenges. Kepler 4-7 is a circumbinary system, planets orbiting both stars of a binary pair. The system has at least 3 planets, including one in the habitable zone. The planets experience constantly varying gravitational forces as the 2 stars orbit each other. The gravitational environment is far more complex than in single star systems, yet the planets remain in stable orbits. Before discovering circumbinary planets, many astronomers doubted they could exist. The gravitational perturbations from 2 stars seemed likely to destabilize planetary orbits, especially for planets orbiting close to the binary pair. But nature found a solution. Stable circumbinary orbits exist beyond a certain distance from the binary pair. Once again, what theory suggested was unlikely turns out to be possible and apparently not uncommon. The Upsilon Andromedae system shows how complex planetary arrangements can become. This system has at least 4 planets, and the orbits are highly inclined to each other. They don't all orbit in the same plane. The planets' orbits are tilted by tens of degrees relative to each other, creating a 3-dimensional orbital configuration unlike anything in our solar system. This arrangement likely arose from gravitational interactions that tilted the planets' orbits over time. Discovering that orbital planes don't always align was surprising. We expected planetary systems to be flat, like records spinning around a star. But 3-dimensional configurations are possible, and they seem to be not uncommon. This adds another layer of complexity to understanding planetary system dynamics. Some systems show evidence of missing planets' gaps in the orbital distribution or dynamical properties that suggest a planet once existed but was ejected. The current planet's orbits might be explained by past interactions with planets no longer present. These ghost planets, wandering through interstellar space, are reminders that we see planetary systems after their chaotic evolution, not in their initial configurations. The solar system itself might have ejected a planet. The NICE model of solar system evolution suggests that the giant planet's orbits shifted about 4 billion years ago, potentially ejecting a 5th ice giant. The rogue planets we detect wandering through the galaxy might include planets ejected from systems like ours during instability events. PSRB 1257+12 represents an extreme system configuration. These planets orbit a pulsar, a rapidly spinning neutron star. The pulsar's intense radiation and magnetic fields create an environment utterly hostile to planets. Yet, not only do planets exist, but they orbit in nearly circular, coplanar orbits, suggesting formation in a disk after the supernova. This system proves planets can form or survive even around the most extreme stellar remnants. White dwarf systems sometimes show evidence of planetary systems too. Observations of polluted white dwarf atmospheres, White dwarfs with heavy elements that should have sunk out of sight suggest these stars are accreting material from disrupted asteroids or planets. Some white dwarfs show periodic dips in brightness, suggesting intact planets still orbit, having survived their star's red giant phase. Planets existing around white dwarfs shouldn't survive the star's expansion to red giant size, yet apparently some do, or new planets form from debris after the red giant phase. These impossible systems teach us that planetary configurations are far more diverse and resilient than we anticipated. Systems we expected to be unstable persist for billions of years. Planets form or survive in environments we thought were too hostile. Orbital arrangements we thought impossible turn out to be merely improbable. Each discovery expands the range of what we know is possible, revealing that the universe is more creative than our imaginations. As you contemplate these impossible systems, imagine the complexity of gravitational interactions in multi-planet systems. Imagine 7 planets orbiting closer than Mercury, locked in perfect resonance. Imagine planets passing within 1 million miles every few months, experiencing strong gravitational tugs, yet maintaining stable orbits. Imagine planets orbiting 2 suns, experiencing constantly changing gravitational forces. These systems shouldn't work, yet they do, teaching us that shouldn't means only that we didn't understand the possibilities. One of the most fundamental relationships in planetary science is between mass and radius. For rocky planets like Earth, as mass increases, radius increases at a predictable rate determined by the compressibility of rock and metal. For gas giants like Jupiter, the relationship is more complex but still predictable, based on the behavior of hydrogen and helium under pressure. These relationships allowed us to predict what types of planets would exist at different masses. Then we found planets that violate these relationships. WASP 107b is the poster child for mass-radius anomalies. This planet has a mass similar to Neptune, about 30 Earth masses, but a radius approaching Jupiter's. Its density is incredibly low, just 0.13 grams per cubic centimeter. Standard models of planetary structure cannot explain how a planet this puffy can exist. The low density implies the planet is almost entirely hydrogen and helium, with minimal heavy elements. But a 3.0 Earth mass core shouldn't be able to capture enough gas to inflate to this size without becoming much more massive. The existence of WASP 107b challenges our understanding of gas capture during planet formation. Either the planet captured gas through a mechanism different from standard core accretion, or it formed with a much larger mass and has since lost significant material, or our models of planetary interior structure are missing important physics. Each explanation has problems, yet the planet exists, demanding an explanation we don't fully have. HATP 32b presents the opposite anomaly. This planet has a radius slightly larger than Jupiter, but a mass about 0.94 Jupiter masses. It's less massive than Jupiter, but more inflated. The planet orbits very close to its star, receiving intense radiation, but the heating alone doesn't fully explain its large radius. Some additional mechanism must be preventing the planet from contracting to its expected size. Many theories attempt to explain inflated hot Jupiters. One suggests that tidal heating energy deposited by tidal forces from the nearby star keeps the interior hot. Another proposes that stellar radiation is absorbed deep in the atmosphere and transported to the interior, preventing cooling. A third invokes magnetic field interactions between the planet and stellar wind. None fully explains all observed cases, suggesting multiple mechanisms might operate. The most puzzling aspect is that not all hot Jupiters are inflated. Some have the sizes predicted by standard models, while others orbiting at similar distances and receiving similar radiation are significantly larger. This suggests that planetary properties beyond mass, radius, and stellar radiation matter. Perhaps atmospheric composition, core size, or magnetic field strength play roles we don't fully understand. Cancri E represents a different mass-radius puzzle. This super-Earth has a radius about twice Earth's but a mass about 8 times Earth's. This gives it a density, suggesting a composition dominated by carbon rather than oxygen-rich silicates. If true, this planet's interior structure would be fundamentally different from Earth's, with a diamond core and carbide mantle replacing the iron core and silicate mantle of Earth-like planets. But confirming this carbon-rich composition is difficult. The mass and radius alone don't uniquely determine composition. Multiple combinations of materials could give similar results. However, if Cancri E is indeed carbon-rich, it would prove that planets can form with radically different compositions depending on the composition of their protoplanetary disk. Earth, formed in an oxygen-rich environment. Cancri E might have formed in a carbon-rich environment, producing a world chemically alien to our experience. Coro T3b blurs the line between planet and brown dwarf. With a mass about 22 times Jupiter's, it's near the deuterium burning threshold, the mass at which an object can fuse deuterium, the dividing line between planets and brown dwarfs. But its radius is only about Jupiter's size. This high density suggests the object has contracted under its own gravity more than typical gas giants, behaving more like a failed star than a bloated planet. This raises fundamental questions. What is a planet? Is it defined by formation mechanism, by mass, by composition, or by some other property? Coro T3b formed like a planet in a disk around a star, but has properties approaching brown dwarfs, which form like stars from gravitational collapse of gas clouds. The universe doesn't care about our classification schemes. It produces objects across a continuum of properties. Toy 1431b, also called Mascara 4b, is one of the hottest and most massive hot Jupiters known. With about 3 Jupiter masses and located extremely close to its star, this planet experiences temperatures around 3000 Kelvin. Despite its high mass, which should cause gravitational compression, and extreme heating, which could cause inflation, the planet has a size close to Jupiter's, neither significantly compressed nor inflated. It sits right at the size predicted by standard models, even though it's in an environment where we might expect deviation. The fact that some planets in extreme environments match predictions while others deviate significantly suggests that multiple competing factors are at play. Stellar heating might inflate a planet, but high mass might compress it. The balance between these effects, plus others we might not fully understand, determines the final size. Each planet is a unique outcome of multiple physical processes, not a simple result of a single relationship. Kepler 7b, HATP 1b, and several other extremely low-density planets form a class called puffy planets. They're all large, low-density gas giants orbiting close to their stars. But even within this class, there's diversity. Some have higher densities than others. Some orbit closer to their stars. Some have higher masses. The range of properties within even this specialized class suggests that multiple factors contribute to puffiness, and different planets achieve similar outcomes through different combinations of factors. These mass-radius anomalies remind us that planets are complex systems, not simple objects following simple rules. The interior structure depends on composition, temperature, pressure, rotation rate, magnetic fields, and probably factors we haven't identified. Each planet is a unique outcome of its formation history and subsequent evolution, not a standard product of a universal assembly line. As you contemplate these size anomalies, imagine planets puffed up like cosmic balloons, barely holding together. Imagine compressed worlds, crushed under their own gravity into sizes smaller than expected. Imagine the complexity of planetary interiors, layers of different materials at different temperatures and pressures, convecting, conducting heat, generating magnetic fields, settling or mixing over billions of years. These anomalies are clues about processes occurring deep inside planets, in regions we'll never observe directly, but can infer from the subtle ways they affect planetary size. Some planets exist not just in unlikely configurations, but in places where they seemingly shouldn't have survived. These are worlds orbiting evolved stars, companions that should have destroyed them, or environments so hostile that planetary existence seems impossible. Yet they persist, witnesses to survival against unlikely odds. V391 Pegasi b orbits a white dwarf star, the collapsed core of a star that once expanded to hundreds of times its original size as a red giant. During the red giant phase, the star should have engulfed and destroyed any planets orbiting close by. V391 Pegasi b orbits at about 1.7 AU within what would have been the star's extended atmosphere during its red giant phase. The planet should have been vaporized. Yet it exists, suggesting it somehow survived engulfment or migrated outward during the star's evolution. Several explanations have been proposed. Perhaps the planet originally orbited farther out and migrated inward after the star became a white dwarf, dragged by interactions with material left over from the star's red giant phase. Or perhaps it did pass through the star's extended atmosphere, but survived due to its large mass, losing only its outer layers. Or perhaps the star's red giant phase was less extensive than standard models predict. Each explanation has challenges, but something preserved V391 Pegasi b through a process that should have destroyed it. Many white dwarfs show evidence of planetary systems. Their atmospheres often contain heavy elements, metals like iron, calcium, and magnesium that should have sunk out of sight within days due to the white dwarf's strong gravity. The presence of these elements suggests the white dwarf is actively accreting material, likely from asteroids or planets torn apart by tidal forces. This implies that planetary systems, or at least planetary debris, commonly survive the red giant phase. Some white dwarfs show periodic transits, suggesting intact planets still orbit. WD 1856 plus 534 hosts a planet about the size of Jupiter orbiting every 34 hours. This planet orbits so close that it would have been deep inside the star during its red giant phase. How it got there without being destroyed is unclear. Perhaps it migrated inward after the star became a white dwarf, spiraling in through an accretion disk. Or perhaps it's the core of a larger planet that lost its outer layers. Either way, its presence defies simple explanations. Pulsar planets present an even more extreme survival challenge. Pulsars are neutron stars, ultra-dense stellar remnants with masses about 1.4 times the Sun's compressed into spheres only about 20 kilometers in diameter. They form in supernova explosions, events so violent that any planets should be destroyed or ejected. Yet we've found planets orbiting pulsars. PSRB 1257 plus 12's 3 planets likely didn't survive the supernova, but formed afterward from the debris. But some pulsar planets might be survivors. If a planet orbited very far from the star before the supernova hundreds of AU away, it might have remained bound despite the explosion, ending up in a highly elliptical orbit around the resulting pulsar. Alternatively, if the star had a companion star, the supernova might have stripped material from the companion, creating a disk from which new planets formed. PSRJ 1719 negative 1438b is an extraordinary example. This planet orbits a millisecond pulsar, a pulsar spun up to extreme rotation rates by accreting material from a companion star. The planet itself appears to be the remnant of that companion star, stripped down to mostly carbon, essentially a diamond-rich stellar core orbiting its destroyer. The planet didn't form through normal planetary processes, but is a stellar remnant transformed into a planet-like object. Some planets orbit in binary star systems where the two stars are very close together. Kepler 16b, 34b, and 35b are circumbinary planets orbiting stellar pairs separated by just 0.2 to 0.3 AU. The planets orbit both stars at distances of about 0.5 to 1 AU. The complex gravitational environment, with two stars orbiting each other while the planet circles both, creates constantly changing forces. That planets can form and remain stable in such environments was surprising. Planets in very wide binary systems face a different challenge. If two stars orbit each other at distances of hundreds or thousands of AU, planets can orbit one star much as they would a single star. But the distant companion still exerts gravitational perturbations over long timescales, potentially destabilizing planetary orbits. Yet we've found planets in wide binary systems, suggesting they're more stable than we initially thought. Some planets orbit at the very edge of their stars' habitable zones, the region where liquid water can exist on a planet's surface. Kepler 22b orbits slightly inside the outer edge of its star's habitable zone. If the star's luminosity varies even slightly, or if the planet's orbit shifts slightly, it could be pushed out of the habitable zone. Yet it's maintained a stable orbit within this narrow region for billions of years, suggesting habitable zones might be more stable than simple calculations suggest. Brown dwarf companions present another survival scenario. Brown dwarfs are failed stars, objects with 13 to 80 times Jupiter's mass that aren't massive enough to sustain hydrogen fusion like true stars. They form like stars from gravitational collapse but never become true stars. Some brown dwarfs host planetary disks and possibly planets. How planets form around objects that themselves are on the border between planets and stars is poorly understood, but observations suggest it happens. The existence of planets around evolved stars, stellar remnants, and extreme environments teaches us that planets are resilient. They survive stellar evolution that should destroy them. They form in environments we thought were too disruptive for planet formation. They adapt to changing conditions over billions of years. Each survivor tells a story of unlikely persistence, of conditions that allowed survival when destruction seemed inevitable. As you contemplate these survivor planets, imagine worlds weathering stellar evolution. Imagine a planet orbiting as its star swells to hundreds of times its original size, the surface temperature soaring as the stellar atmosphere approaches. Imagine somehow surviving this phase, perhaps by migrating outward, perhaps by losing outer layers while preserving a core, perhaps through some mechanism we don't understand. These planets are veterans of cosmic catastrophes, witnesses to events that would have destroyed less fortunate worlds. Beyond anomalies in orbit, density, and configuration, we've discovered planets whose very composition defies our expectations. These are worlds made of materials we didn't anticipate, in combinations we didn't predict, challenging our understanding of what planets can be made from. HD 149026b is a Saturn mass planet with a core far larger than any gas giant should have. Standard models suggest gas giants should have cores of 10 to 20 Earth masses, surrounded by thick envelopes of hydrogen and helium. But HD 149026b appears to have a core of 70 to 110 Earth masses, roughly the mass of Saturn itself, wrapped in a relatively thin gas envelope. This massive core shouldn't exist according to our formation models. How can a planet accumulate such an enormous core? Perhaps it formed in an unusually metal-rich region of its protoplanetary disk, where solid material was far more abundant than typical. Or perhaps it formed as a normal gas giant but underwent a giant impact that delivered additional core material. Or perhaps our estimates of core mass are wrong, affected by factors we don't understand. Each explanation has challenges, but the planet exists, demanding an explanation we struggle to provide. WASP-12b, discussed earlier for its death spiral into its star, also shows compositional anomalies. Spectroscopic observations suggest the planet's atmosphere is enriched in carbon relative to oxygen, with a carbon-to-oxygen ratio greater than 1. In our solar system and most known exoplanets, oxygen is more abundant than carbon. A carbon-rich atmosphere would dramatically alter the planet's chemistry, potentially forming exotic compounds like titanium carbide instead of titanium oxide, silicon carbide instead of silicon dioxide. If WASP-12b is truly carbon-rich, it suggests formation in a carbon-enriched region of its protoplanetary disk, or perhaps capture of carbon-rich material later in its evolution. Understanding how to create carbon-rich planets requires reconsidering the chemical composition of protoplanetary disks and how that composition varies. K222b, also called EPIC 2 016-37175. B may be the first discovered planet, evaporating so rapidly that we can watch it happening in real time. This small planet orbits extremely close to its star, completing an orbit every 9 hours. Observations show a cloud of debris around the planet, suggesting its rocky surface is being vaporized and blown away by stellar radiation. We may be witnessing a planet in the process of being destroyed, reduced to nothing more than a bare core or even complete disintegration. The discovery of an evaporating planet raises questions about planetary lifetimes. How long can a planet survive at such close orbital distances? Are there populations of planets that have already been completely destroyed, leaving no trace? Might some planetary systems we observe be missing planets that were destroyed long ago? The universe of possible planetary fates expands with each discovery. BD plus 202457 hosts planets or planetary remnants that appear to have very high metal content. The host star itself is unusually metal-rich, suggesting the entire system formed from material with high concentrations of heavy elements. The planets orbiting this star would have formed from this metal-rich material, potentially creating worlds with compositions radically different from anything in our solar system. Metal-rich planets might have thicker crusts, different tectonic regimes, unusual magnetic field generation, and chemistry unlike Earth's. Life on such worlds, if it could exist, would have access to abundant heavy elements, but would need to adapt to whatever unique chemistry these compositions create. Understanding metal-rich planets helps us appreciate the range of planetary chemistries possible. Some white dwarf systems show evidence of asteroids or planets with compositions unlike anything in our solar system. The heavy elements accreting onto white dwarfs come from disrupted planetary bodies, and analyzing those elements reveals the body's compositions. Some show high concentrations of calcium or magnesium, others are iron-rich, some have unusual ratios of different elements. These composition measurements from destroyed planets give us information about planetary interiors we could never obtain otherwise. When a planet is torn apart and its material accretes onto a white dwarf, we can analyze that material spectroscopically, learning about planetary differentiation, core mantle boundaries, and compositional layers. Destroyed planets are teaching us about planetary structure. GD61 is a white dwarf whose atmosphere shows evidence of accreting a water-rich asteroid or planetary fragment. The high water content suggests the parent body formed beyond its system's frost line, where water ice was stable. This provides evidence that water-rich bodies exist in other planetary systems, that water might be common throughout the galaxy, and that the building blocks for life might be widespread. The existence of water-rich bodies around other stars has profound implications for astrobiology. If water is common, and if organic molecules are common, as observations increasingly suggest, then the raw materials for life might exist in many planetary systems. Whether those materials actually produce life is a different question, but at least the ingredients are there. WASP 76b, discussed earlier for its iron rain, also shows atmospheric composition anomalies. Besides iron, spectroscopic observations have detected vanadium, chromium, calcium, and sodium in the atmosphere. The day side is hot enough to vaporize many metals, creating an atmosphere rich in metallic vapors, unlike anything in our solar system. The chemistry in such an environment would be entirely alien to Earth-based intuitions. 55 Cancri E, potentially the diamond core planet, also shows evidence of atmospheric volatiles. Despite surface temperatures around 2,400 degrees Celsius, the planet appears to have an atmosphere, possibly including hydrogen cyanide, a molecule that's toxic to Earth life, but might be common in carbon-rich environments. Understanding the chemistry of carbon-rich atmospheres is a new frontier in planetary science. These compositional mysteries remind us that planets can be made from many different recipes. Earth's specific composition, iron core, silicate mantle and crust, water oceans, nitrogen-oxygen atmosphere, is one possibility among many. The universe creates planets from whatever materials are available, in whatever proportions exist locally, producing a diversity of compositions we're only beginning to catalogue. Each compositional type implies different surface conditions, different atmospheric chemistry, different possible mineralogies, different potential for life. Carbon-rich planets would have different geochemistry than oxygen-rich planets. Metal-rich planets would have different internal structures than metal-poor ones. Water-rich planets would evolve differently than dry planets. The composition determines much of a planet's character. As you contemplate these compositional mysteries, imagine worlds made of materials in combinations we've never encountered. Imagine carbon-rich planets with diamond cores, silicon carbide mantles, atmospheres of exotic carbon compounds. Imagine metal-rich worlds with thick iron mantles, unusual magnetic fields, surface chemistry dominated by heavy elements. Imagine the diversity of planetary recipes the universe employs, each creating a unique world with its own properties and possibilities. We've toured planets that shouldn't exist, hot Jupiters that violated our formation theories, super-Earths in a forbidden mass range, retrograde worlds orbiting backward, inflated planets defying our understanding of structure, systems arranged in impossible configurations, survivors of stellar death. Each discovery forced us to expand our understanding, to admit our theories were incomplete, to embrace cosmic complexity we hadn't anticipated. But these planets don't actually break physics. They follow the laws of physics perfectly. What broke was our understanding of what physics allows. This distinction matters. The laws of physics, conservation of energy and momentum, gravity, thermodynamics, quantum mechanics are absolute. They govern all matter and energy everywhere in the universe. They cannot be broken. But our human understanding of how these laws operate in complex systems is always incomplete. We build models, make predictions, test them against observations. When observations contradict predictions, we don't discard the laws of physics, we improve our models. Hot Jupiters taught us about planetary migration. Before their discovery, we knew migration was theoretically possible but thought it was rare. Hot Jupiters proved it's common, forcing us to incorporate migration into all our formation models. Our understanding evolved, physics didn't change. Super-Earths taught us that the mass range between rocky planets and gas giants, which seems forbidden in our solar system, is actually the most common planetary type. Our solar system is the anomaly, not other systems. We had generalized from one example always a dangerous practice. The universe taught us better. Retrograde planets taught us that planetary systems are dynamically violent, undergoing instabilities that can flip orbits. We thought systems were stable after formation. We learned they're stable only after settling down from initial chaos. Our timescale understanding expanded. Every anomalous planet taught us something. That's the beauty of these worlds that break physics. They're not breaking anything. They're teaching us. Each discovery is a gift of knowledge, an opportunity to refine our understanding, to see the universe more clearly. The fact that planets surprise us repeatedly shows that we still have much to learn, and learning is exciting, not frustrating. Consider how much planetary science has advanced in just 3 decades. Before 1995, we knew only one planetary system, ours. We had theories about how planets formed and what types should exist based on this single example. Then we began discovering exoplanets, and almost every discovery challenged something we thought we knew. Hot Jupiters, super-Earths, mini-Neptunes, puffy planets, retrograde orbits, circumbinary planets. Each one initially seemed impossible. Now, 3 decades later, we've discovered thousands of exoplanets. Our understanding has evolved dramatically. We know planetary systems are diverse, that formation and evolution are complex processes with many possible outcomes, that our solar system represents one path among many. We've learned humility. The universe is under no obligation to match our expectations. This progression of understanding is how science works. We develop theories based on available evidence. When new evidence contradicts those theories, we revise them. The revised theories make new predictions, which we test with further observations. The cycle continues, each iteration bringing us closer to understanding reality. We never achieve perfect understanding. There's always more to learn, but we continually improve. The planets that broke our physics remind us that nature is the ultimate teacher. No matter how sophisticated our theories, how elegant our mathematics, how certain our predictions, nature has the final word. When observation and theory disagree, observation wins, always. This principle has guided science for centuries and will continue to guide it. There's something comforting about this. It means the universe is knowable but not yet known. There are discoveries waiting to be made, mysteries waiting to be solved, anomalies waiting to teach us. The fact that we still find surprising planets means we're still learning, still growing in our understanding. Science isn't finished, it's ongoing. Future discoveries will undoubtedly reveal new types of planets we haven't imagined. Perhaps we'll find planets orbiting in configurations we currently think are impossible. Perhaps we'll discover planetary masses or densities outside the ranges we think are possible. Perhaps we'll find systems so complex they challenge our computational abilities to model. Each such discovery will expand our understanding further. The search for exoplanets continues. New telescopes, more sensitive instruments, better analysis techniques all enable us to detect smaller planets, planets farther from their stars, planets around fainter stars. Each technological improvement reveals new planets, new configurations, new challenges to our understanding. The universe's diversity seems inexhaustible. As we learn more about exoplanets, we learn more about our own solar system. Every anomalous planet discovered elsewhere helps us understand what's special or typical about Earth, Jupiter, Saturn, and the others. We can now see our solar system in context as one example among many, with its own unique features and its own typical features. This cosmic perspective is invaluable. These planets that broke physics also remind us that science is a human endeavor. Our theories reflect our current understanding, our assumptions, our biases. We build models based on what we know, but we don't know everything. Each discovery reveals gaps in our knowledge, areas where our understanding was incomplete or wrong. This isn't failure, it's progress. Recognizing what we don't know is essential to learning. As you contemplate these reality-defying worlds, let them inspire not confusion but wonder. Yes, they challenged our theories. Yes, they forced us to reconsider fundamental assumptions. Yes, they revealed that we didn't understand planets as well as we thought. But they also revealed that the universe is more interesting, more diverse, more complex than we imagined. They're invitations to deeper understanding, to continued exploration, to embracing the unknown. The universe is full of surprises. That's not a problem, it's a feature. It means there's always more to discover, always more to learn, always new mysteries to solve. The planets that broke physics are not enemies of understanding, but enablers of it, challenging us to think more deeply, to question our assumptions, to remain humble before the vast complexity of nature. As our journey through planets that break physics draws to a gentle close, let us reflect on what these impossible worlds teach us about the universe, about science, and about ourselves. The planets we've explored tonight, hot Jupiters, super-Earths, retrograde worlds, inflated giants, compact systems, survivor planets, all seemed impossible before we discovered them. Each violated something we thought we knew, challenged some assumption we thought was fundamental, forced us to expand our understanding of what's possible. Yet none of them break the actual laws of physics. They're not supernatural or magical. They simply exist in configurations we hadn't anticipated, following the laws of nature we're still learning to fully understand. Our theories broke, reality didn't. This distinction is profound. It means the universe is comprehensible but requires humility and openness to understand. We must be willing to revise our theories when observations contradict them. We must remain open to surprises, willing to admit when we're wrong, eager to learn from nature's teachings. The diversity of planets discovered in recent decades is staggering. Hot Jupiters orbiting in days, super-Earths and mini-Neptunes in the forbidden size range. Planets orbiting backward, tilted, in highly elliptical orbits, planets around binary stars, dead stars, violent stars. Planets as puffy as styrofoam, as dense as iron, as large as Jupiter, as small as Mars. Every new discovery adds to the catalogue of cosmic possibilities. This diversity arises from the complexity of planetary formation and evolution. Planets form from disks around young stars, but the details, the disk's mass, composition, temperature, structure, lifetime vary widely. Planets migrate through these disks, interact gravitationally with each other, exchange orbital energy and angular momentum. Some collide, some are ejected, some end up in orbits far from where they formed. Systems evolve over millions of years, settling into configurations that depend on countless details of their unique histories. The result is a universe of planets more varied than we imagined possible. Our solar system, once thought to be typical, now appears to be somewhat unusual. Our orderly arrangement of rocky inner planets and distant gas giants is common but not dominant. Many systems have hot Jupiters or compact systems of super-Earths or planets in configurations unlike ours. Earth itself, in the habitable zone with liquid water and life, might be unusual among planets. Yet every planet, no matter how anomalous, follows the laws of physics. Gravity pulls them into orbits. Conservation of angular momentum governs their spins. Thermodynamics controls their heat flows. Quantum mechanics determines their atomic structure. The laws are universal and absolute. Our understanding of how these laws combine to produce planets is what has evolved. This gives us confidence in science as a method. When our theories fail to explain observations, we don't abandon science, we improve our theories. We don't reject the laws of physics, we refine our understanding of what they allow. Science is self-correcting, continually improving as new evidence accumulates. The planets that broke our physics are evidence that this process works. As we discover more about exoplanets, we also learn more about the potential for life elsewhere. Some anomalous planets orbit in habitable zones. Some super-Earths might have conditions suitable for life. Some tidally locked planets might have habitable twilight zones. The diversity of planetary types increases the range of environments where life might exist, expanding our conception of habitability. Conversely, the rarity of Earth-like planets reminds us how special our world is. Earth orbits in the habitable zone at the right distance from a stable star. It has a mass large enough to retain an atmosphere, but not so large as to capture a thick hydrogen-helium envelope. It has liquid water, continents, a magnetic field, plate tectonics. Many factors had to align to create Earth's hospitality. The anomalous planets show us how many ways planet formation can produce non-Earth-like worlds. The future of exoplanet research is bright. New telescopes like the James Webb Space Telescope are characterizing exoplanet atmospheres, detecting molecules that might indicate life. Future missions will image exoplanets directly, seeing them as points of light separate from their stars. Ground-based telescopes with adaptive optics are finding more planets, including smaller ones and those at greater distances. Each new discovery adds to our understanding. We will undoubtedly find more planets that challenge our theories. Nature still has surprises in store. Perhaps we'll discover planets even more anomalous than those we've found so far. Perhaps we'll find configurations we currently think are impossible. Each such discovery will expand our understanding further, teaching us new physics, revealing new possibilities. As you drift toward sleep, let your mind wander among these impossible planets. Imagine hot Jupiters blazing mere million kilometers from their stars. Imagine super-Earths with gravity 3 times Earth's. Imagine planets orbiting backward, defying the expected direction of motion. Imagine systems with 7 planets closer than Mercury, locked in perfect resonance. Imagine planets surviving their stars' deaths, witnesses to cosmic cataclysms. But then return to Earth, return home. Feel the familiar pull of gravity, precisely 1 g. Feel the atmosphere at comfortable pressure, breathable and clear. Know that above you, the sky follows predictable patterns, day turning to night in 24-hour cycles, seasons following their ancient rhythms. Earth is a planet that doesn't break physics, it follows it comfortably, existing in a configuration that's somewhat unusual but perfectly stable. We are privileged to live in an era of discovery. We're the first humans to know that planets are common, that most stars host them, that planetary diversity is vast. We're learning that our intuitions about what's possible were too limited, that the universe is more creative than we imagined. These anomalous planets are gifts of knowledge, each one teaching us something new about how nature works. The planets that break physics don't actually break anything. They break only our assumptions, our limited understanding, our too narrow conception of possibilities. They reveal that the universe is larger, stranger, more wonderful than we knew. And in doing so, they invite us to keep exploring, keep learning, keep expanding our understanding. Rest well, cosmic explorer. Dream of impossible planets in impossible orbits. Dream of worlds that challenge understanding and expand it. Dream of the vast diversity of the cosmos, of planets we've found and planets yet to discover. And wake grateful that we live in a time when humans can know such things, when we can observe distant worlds and learn their secrets, when the universe reveals its complexity to patient observers. The impossible planets await our continued study. They have more secrets to reveal, more lessons to teach. But tonight, as you rest, know that the most important lesson they offer is this: the universe is knowable but endlessly surprising. comprehensible but never fully understood, governed by laws we can discover but applied in ways we're still learning. And that is no small thing in a universe of hot Jupiters and retrograde worlds, of super-Earths and survivor planets, of diversity beyond imagination.